I'm starting plotting, so if you want, you can get at the end.
Okay, fine. Let's
So, is the screen visible?
can't.
Yes, yes.
Yes, dear.
All right.
Uh,
So we are doing this for structure analysis for mids.
Yes.
All right. So for mids, there are two topics. Basically, we have two topics. First one is force method, and the second one is slope reflection method. I'll try to cover a force method today. Then we can have another one for slope reflection.
Yeah,
All
inshallah.
right.
All
Inshallah.
right, all right. Let's go through first method today completely.
Okay. So force method. First, I'll just some steps for force method. I find it much easier to remember those steps because in paper, if we just go through the examples, we forget one step or something, then that's difficult. So the steps would be, first we'll calculate primary and secondary or redundant structures. We'll go through these in a moment. So just I'm writing so we can refer it back. Primary, secondary, or redundant structures. Then we'll find the compatibility equations. And then we'll calculate deflections. Basically, these three steps are new steps. These one. The rest of the steps, they are exactly the same that we have done in ESA. Like we have done, fourth one is reactions. We already calculated it in ESA and also in mechanics of materials. Then we find the shear force diagram or bending moment diagram. Or in case of frame, also axial force diagram. Frames. So these are 5 steps. First 3 are new ones that are exclusive to force method. The rest 2 are we are doing it from mechanics of materials. Same, we calculate the directions and when we draw the shear force diagram and bending moment diagram. So steps are clear. First we draw the structures, then we write the compatibility equations, then we calculate deflections. All right.
Okay.
Yes.
So let's start with the question. Suppose this is a beam. It's a simple beam. Just 1 minute, done. Okay, sorry for the interruption. It was downtime. So this is a beam. All right. This is a simple indeterminate beam. Okay. Am I audible? Is my voice coming?
Yes, brother. Yes, brother.
Okay, okay. I thought some direct connection issue. All right, this is a simple indeterminate beam. So we have to find its force reactions, this By and Ay and moment at A, and we have to calculate it by force method. So our first step was we have to resolve it into primary and secondary structures. So for that purpose, we'll do this. So here we have two reactions in this sport at A. At sport A, there are two reactions. We ignore horizontal reaction for beam because there is no axial force in beam. So we ignore the horizontal ones. And there is one reaction at B sport. Is that okay? Two reactions, a moment reaction and a vertical force reaction at A, and one reaction at B. All right. So our formula for beams is R minus 2. This is the formula. For beams, it is R minus 2 because we are ignoring the horizontal reactions. So we have three reactions in total, 2 at A and 1 at B. 3 minus 2 is equal to 1. So our beam is indeterminate to first degree. The degree of indeterminacy for this beam is 1 degree. Okay. How we calculate? Have you all got this? How we calculate degree of indeterminacy for beam?
Yes, brother. Yes.
R minus 2. Okay, we'll do this for this one. Here we have two reactions at A because we are ignoring the horizontal ones. Actually, we have three reactions at fixed sport like this. We have a vertical reaction, we have a horizontal reaction, and we have a moment reaction. But we are ignoring this horizontal one for beams. For beams, there is no axial force, so we ignore this. We'll consider this in frames, but in beam we ignore this. So two reactions at A and two reactions at C. So that will become 5 minus 2 is equal to 4 minus 2 is equal to 2 degree. So this is indeterminate to second degree. Similarly, here we have one reaction, two reaction, and three at A. 1, 2, and 3. We are not ignoring horizontal because this is a frame. We ignore it only in beams. We don't ignore it in frames and in trusses. So here the formula is R minus 3 or 6 minus 3 is equal to 3. It is indeterminate to third degree. So have you all got this? First step in the first step.
Excuse me. Excuse me.
Yes.
Can you repeat this again? Just that.
Sorry. Which one?
Go back that one.
For frames?
Yeah.
All right.
Yeah, this one.
This is a frame. We have two fixed supports, one at A and one at D. All right. So we have two fixed supports, one at A and one at D. For fixed support, there are three directions. One is vertical, one is horizontal, and one is moment traction. So there will be three directions here and three directions here. You can assume the direction arbitrarily. There's no I am assuming it is clockwise and in right and upward. But you can also put the direction as opposite. There is no issue. So we have 3 direction at A, 3 direction at D. We ignore horizontal direction for beams because there is no axial force, but we consider it for frames. There is axial forces. So in beam, our formula was R minus 2 because there are 2 equilibrium equations for beams. Sorry. Yes. There are 2 equilibrium equations. One is summation Fy is equal to 0 and the other one is summation moment at a point is equal to 0. Summation Fx is not, we are not considering this, so this is 2 equations. So in frame, there are 3 summation Fx, summation Fy and M. Summation Fy and M. We consider all of these 3. So our formula would become R minus 3. So we have 6 directions. 1, 2, 3, 4, 5, 6. 6 directions in total. 6 minus 3, that is equal to 3. So our frame is indeterminate to 3rd degree. Or degree of indeterminacy for this frame is 3. Okay?
Thank you. Thank you.
Okay. No. This was the part of our first step. We are resolving this. We are doing this. We are resolving our structure, our question to in primary structure as well as redundant structures. So first we find the degree of indeterminacy. Now we are going to resolve it. So our in this case, for our first example, beam is indeterminate to first degree. So we'll have to remove one direction. Basically, this degree of indeterminacy gives tells us how many directions we have to remove. So in this case, as it is 1, so we are going to remove 1 direction. In this case, we are going to remove 2 directions, and in the frame case, we are going to remove 3 directions. So this is that is why we have calculated this degree of indeterminacy. So I'll try to draw 2 cases. This one is first and this one is second. So let's see. In the first case, we have removed the direction at B. Okay, we have removed the support at B, which means we have removed the direction at B. So this makes our total direction 3 or 2 in case of beams here. So this will make our beam determinate as well as stable. So when a structure, we resolve a structure into a structure that is determinate as well as stable, we call that structure as primary structure. I'll write it. Primary structure, it has 2 properties. It is determinate as well as it is stable. Stable in sense that we cannot make a structure like this, 2 roller supports. This is, although this is determinate, but it will deflect. It will not deflect. It will move in the direction of force. So it is not stable. So we have 2 conditions for primary structure. We have it has to be determinate and it has to be stable. Okay. So I've created here 2 structures that are determinate as well as stable. So this is a cantilever beam. It is determinate, and this is a simply supported beam. It's also determinate. Okay. All right. This is an important step as the whole question is going to depend on this step. How we are going to resolve this our question into determinate structure. So afterward, all our reactions will be based on this. For example, in this one, we have removed the supported B, so our reaction will be By. But in this second case, we have moved the fixed support and converted into hinge support. Then our reaction will be at moment at A, some sort of moment. Clear? Is this step clear? Is this clear?
Yes, babe.
Yes, brother.
All right. So it is our own choice that how we are going to resolve this. I mean that we can either create it as a fixed port and a cantilever beam or a roller range port as in a simply supported beam. So it's our own choice, but I would suggest that you go with the first one, this cantilever one, because writing equation for this port is very much easier than this one. We have to calculate its traction first. In this case, we don't have to calculate traction at all. So it's your own choice. Both of them will work, but it is preferable that you use the first one. So we have resolved it into a primary structure. This is a primary structure. It has applied load, all the applied loading, but it is stable as well as determinate. Thus, now we are going to add the redundant structures. As the degree of indeterminacy is 1, so only one redundant structure will be there, and it will simply consist of the same primary structure, but a unit load applied at where we have removed the support. So we apply By is equal to 1. So this is just a primary redundant structure. We have resolved our structure into a primary structure and a redundant structure because there was degree of indeterminacy was 1, so we have only one redundant structures. If it was, we'll go through second and third one next steps. So is this clear? That primary and redundant structure we have calculated. Here, in this example, we have second degree of indeterminacy. So we can just resolve it again into cantilever beam plus 2 redundant structures. 1 and this one is 2. R1, R2. So the number of redundant structures, they depend on the degree of indeterminacy of our beam, of our structure. How many degree it is indeterminate, we draw that many redundant structures. So in this case, we remove the vertical force at C as well as a moment at C. So in redundant structure, we'll just put these here. This is By, oh sorry, Cy, and this is MC. Okay. We just where we remove our support, we just place a reaction at that place, and that magnitude of that reaction should be 1. It should be a unit load or unit moment. In our frame case, we'll do this, something like this. This is our primary structure. Again, I have resolved it into a cantilever, only one fixed port, plus 3 redundant structures. 1, 2, and 3. So we have removed these horizontal direction, vertical direction, as well as a moment direction at point D. So I'll just place forces here. Horizontal force HD, vertical VD, and a moment MD. This was our primary structure, the top one, 26 and 48. So clear how we are going to resolve the primary structures and redundant structures. We have done cases up to up to structure that have degree of indeterminacy as 3. So up to this, I hope that paper will come up to this, because fourth one would be very much lengthier. It will have almost 24 equations. So that's impossible to do in an hour. That's the whole time allotted to us. So at most, a third degree would come, but most probably a second degree would come, as we have another question to slope deflection method too. So it depends on practice that how you in how much time you complete this question. So this was our first step. Clear? We have resolved our question into primary and as well as redundant structures. Okay.
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 All right. So our second step. We have to write the compatibility equations. So it's simple. You can just memorize them if you don't understand, couldn't understand for some reason. You can just memorize them, but it's very simple. Just draw a deflected diagram of primary structures. This is a deflected diagram. They evaluate something delta B. Because it's deflection and at B point, so I'm calling delta B. And this and the deflection of the second beam would be something like this. Because the force is pushing it upwards, so it would deflect upwards, and we are naming it delta dash BB. So the first B stands for the point where we are measuring the deflection, it is B point. The second B stands for force, where the force is acting. The force is acting also at B, so we'll call it delta dash BB. So we know that here in the original question, at roller sport there can be no vertical deflection. Roller sport allows horizontal deflection, but it does not allow vertical displacement. So we know that here deflection is 0, here deflection is delta B, here deflection is delta dash BB. So we can write it as 0 is equal to delta B minus delta dash BB. Why negative sign? Because these both deflection are in opposite direction. Delta B is downward, delta dash BB is upward. So we can put negative sign with any of one. We can write minus delta B plus delta dash BB. It does not matter. And 0 because here the deflection is 0. Okay, this is just a compatibility equation. And a formula to remember that deflection is equal to flexibility multiplied by force. P is a formula. Okay, deflection is equal to flexibility multiplied by force or load. What is flexibility? Flexibility is deflection produced by unit load. Flexibility is equal to deflection over P. So when P is 1, so flexibility is equal to deflection. So we can define deflection produced by unit load. So we can write it delta B minus delta BB. We can write it FBB into BY. So we can get BY is equal to delta B over FBB. Okay, this is compatibility equation for first degree of indeterminacy. Just the deflection at the same point and the force at the same point. The flexibility of produced by that force and the deflection we divided it, and then we get the BY or support reaction at B. For a second case, in this second case, we'll get two compatibility equations because the degree of indeterminacy is 2. So let's draw. This is our primary structure. We can call it. This is a point C. This is our point B. So we can call this deflection at delta C. This deflection here at delta B. This force these forces are upward, so it will cause it to deflect in this way. We can call this at delta dash cc because it is deflection at point C produced by load at point C. And here, this movement is rotating this beam in clockwise direction, so it will deflect again downwards. So this will, we can call this we can call this as a deflection at CC. We can call it as delta dash C and alpha. We get this deflection at C from moment acting at C point. Or we can, if you want to write it in the long method, you can write it C delta and MC. That we are getting it from moment at point C. Okay, this is only notation. We can use any one. Doesn't matter. So our equation would become first equation. This at point C, the deflection. Here we have 0 because fixed force is equal to delta C downwards minus delta C, delta dash CC upward, delta dash CC plus delta dash C alpha. Deflection produced by unit moment at point C. Alright. We are just equating these deflections at here in original structure and here in primary structure as well as redundant structure. If we use this formula, then we can get plus FCC into CY plus this one is flexibility. We can write at flexibility alpha into MC. One would be our equation 1. Okay. We are just equating the deflection at point C. Now, second equation, we can equate rotation at point C because at fixed force theta is equal to 0. It does not allow rotation. Delta is also 0 in horizontal as well as vertical direction, and theta is also 0. So we'll get something like this. Here we have 0, and here we can assume this is clockwise and theta C. Theta C. This is counterclockwise. We can calculate minus theta dash CC, and here this is clockwise. This one is clockwise. We have to draw arrow from the original structure. Plus theta dash C alpha. We can call it at any name. Alright, this one is our second equation. We can expand it also minus alpha CC into CY plus FC alpha into MC. Are the equation clear? Or we are writing them? Because we have to only do these two steps here. These two steps, primary structure and compatibility equation. We only have to do these two steps. The rest of the steps they are already done. We have already calculated one deflections in ESA. Here we have to calculate a bunch of them together. So that's why I referred it as almost a new step, but we have done it somewhat in before. So here we have done two equations. All right. Okay.
Okay.
So this is our third structure. Reset. Let's draw it. This is our primary structure. So how do you think that it will deflect? Something like this. This horizontal force will cause it to move rightwards. This 96 will cause it to move downwards for this time. And then we can draw them like this. So this is approximate elastic curve of this structure. It does not have to be exact. You can assume any one. So it does not matter. But if you assume the right one, then your all answer will come positive. If you assume something incorrect, then that answer will come as negative. There will be no difference of any magnitude in, only there will be a difference of direction. So this is a question. We can call this is horizontal deflection, delta dh, deflection at d in horizontal deflection. This is vertical, this one from the elastic curve to this point, origin point. This is vertical deflection delta dv, and this rotation of structure is theta d. Okay, we have just written the names of the deflections at point D. In similar manner, we can write for other. This one is was our original structure 1. This one is second, and this one is third. 3 because the degree of indeterminacy is 3. So again, draw the reflected shapes. The same one you have drawn for this. For the primary structure, draw the same one here. This one we have drawn. So we'll call this at delta dash dh. Deflection at d in horizontal deflection by horizontal force. Or we can first write hd here, vd here, and md here. So because our frame was moving from towards left side, this red line is towards left original frame. That's why we have written HD in left direction. So it's best if you draw elastic curve and then write the equations. Then there will be no sign issue later on. As in this case, look, this is our original frame, and this one is a deflected. This has moved downwards. So we have written VD as downward, and this has rotated in clockwise direction. We have written MD as clockwise. All right. So we have to write all the deflection equations. This is delta dash dh, deflection in horizontal direction at d caused by horizontal force at d. This is delta dash dh by dv. This is delta dash dh by alpha d by moment at d. Similarly, at this point in vertical direction, delta dash dv, this is vertical displacement by dh force. Del dash dv, vertical displacement by vertical force. Del dash dv alpha d, vertical displacement by moment. And finally the rotation, this we can call it theta dash d delta, rotation at d caused by dh. Theta dash d delta by dv, rotation at d caused by dv force, vd or dv. Theta dash dd, this rotation at d point caused by md, moment at d. Is this clear? Because this is the most important step. The compatibility equation we have to derive. This is the most important step in this case. If we have written there correctly, then there will be no issue later on. No sign issue or something like that. All right. So just recap. We first calculate. We have a question. We written how it is how much indeterminate to which degree. Then we draw the primary structure as well as the redundant structures. The number of redundant structure would be equal to the number of indeterminacy, the degree of indeterminacy. How much indeterminate is our structure? We have written the different deflection parameters pH, dV, and theta. This is in primary structure and in first redundant structure, second and third. In first one, we applied horizontal force at D, applied vertical force at D. Third one, we applied moment at D. All equal to 1. These are unit forces and unit moments. So this deflection was called by HD force. This one was called by BD force, and these three were called by MD force. Are you following me up till now? Is it clear? We have done 2 steps. We have derived the primary structure as well as the redundant structures, and we have written the compatibility equations. We have not written for this structure. We can write something like this. The deflection at this point is 0, so we can write it 0 is equal to horizontal dh. First we are equating the horizontal displacement, so we can write dh delta dh this one is delta dash dh delta dash dh dv. This is delta dash dh alpha d delta dash dh dh plus delta dash dh dv plus delta dash dh and alpha d. So this one was in primary structure. This one is first redundant structure, second redundant structure, third redundant structure. Okay. We are just equating them. Similarly, for vertical displacement, we can write as delta dv plus delta dash dv by dh plus delta dash dv by dv plus delta dash dv by alpha d. If you have solved 2-3 question, minimum 2-3 question, you can write it as it is. You know, I mean, I remember this, that this will be written as this. So that's why I said at first that you can just memorize them. They will be written like, all of them would be like this if the question is same. So this one is theta t plus the rotation at T point by dh force plus rotation at D point by dv force plus rotation at D point by moment at D. So these are 3 compatibility equations because our structure was indeterminate to 3rd degree. Okay. We have just written the compatibility equations. Now we have to calculate deflections. Deflection we have to use just simple unit load members, unit load method. I hope you all remember them. Unit load method, Castiglione method. from the last semester, ESA. It was simple that we calculated moment at this structure, primary structure, then moment produced by unit force, then we put it as mm over EI and integrated it 0 to L, where L is the limit of the part of the beam for which, or frame for which we are finding the deflection. This is deflection formula. Remember it? For beams and frames. For trusses, it was NNL over EA summation. We calculated NNL in a tabular form, and then we summed it at the end. So for this question, the first question, we can just calculate delta P and FBB and place the values. Should I calculate here, or you can do unit method? We have done it in ESA. Hello.
I think. What about other? Is it okay? Will you do in your own?
Sorry. Please.
No, I think. Yeah. I think the other guys also having no issues with it. They also have done ESA. I think ESA paper has been already given.
Yes.
So let's keep going on. Yeah, let's keep going on.
Okay. So for first case, it would be no issue. We can just simply calculate. These are two values we have to calculate. You can just apply.
Yes.
For the second one, we have, let me highlight, delta C, FCC, FC alpha, delta C. These are 6 variables here. We have to calculate the values of 6 deflections. So it's preferable that you write it in a tabular form. Something like this: member, origin, limit. For example, member would be AB. This one first member AB. Second member would be BC. We can take limit any. For example, if we are cutting section like this for B section, we can take limit C or B. It doesn't matter. But if you take limit as B, then you have to calculate this port direction before. So if you take at C, the question will be much more simpler. That's why I said that first that cantilever beams are much simpler to solve. So we can, if we take it as C, origin C, and for BC, we can also take it as C. This is our beam. B point, C point. We are cutting section in B, C portion, and if we take origin at C, then this would be X. And for AB portion, this would be our X, as we are still taking the origin as C. All right. Our length would be, limit would be 0 to 3, because this was 3. This is also 3, but we are taking from this to this. AB portion is from B to A. So from here, it will be 3 to, oh sorry, this would be 0 to 3. BC portion is 0 to 3, and AB portion would be from here to here. But we are taking the distance from here, from point C. Origin is at point C. So our distance will be 3 to 6. 3 to 6. Afterwards, we can write the moment equation for primary structures. Just like this is our question, 50 and 3 and 3. So here, if if we cut a section like this here for BC portion, no force is here, nothing. There is nothing here, so you can just place 0 here. But for AB portion, if we cut a section like this is 1 is our x. So this 50 is moving downwards at this and this. So this one was 3, this one would be x minus 3. Because the total one is x, and this is, we know it is a 3, so this one will be x minus 3. So minus 50 into x minus 3. Why minus? Because it is a downward force. Just consider all upward forces as positive and all downward forces as negative. That make it much more simpler.
Brother, in here movements in AB section, the movement should be minus 50 multiplied by
Oh, sorry.
the 0, I think.
I'm thinking BC is upward and AB is downward. Sorry. Actually,
Okay.
I'm solving being from here now, from the right portion. So I'm writing the equation first for BC.
Yeah,
BC would be 0, and this would be minus 50 into x minus 3. Thank you. All right. Then we have a column for first student structure. This one is first student structure. Then we have a column for our second student structure. We have to calculate moment equation for both of them. You can write m. It was vertical force. We can write md and v, and the other one we can write md theta. It was a rotation force. So this one was our C1 upward direction. This one is 1, and this one is our second structure 1. So this is point. In both of these cases, both would be same because there is no in between. B, C, C, C. So first regional structure. This one is x. So 1 into x. Why we are writing it as positive? Because it is an upward force. Similarly, for this portion, again this is x, and 1 will be multiplied with x. Again, this will become 1x. Alright, this one is very much simpler. And in this case, there is no force at all. So our moment would become 1. This moment will only come, there is no force apart from this. Okay. So these one were columns. The next column would, after this column, we have to calculate m into mdv and integrate it. The second column would be m into m d theta, again integrated. Third column would be m dv square and integration. Fourth would be m d theta square and integration. The last one would be m dv to m d theta and integration. Basically, I have multiplied this m with this one first and then this one, and we have done integration here. Okay. Then we have squared these individually. Individually, we have this one squared and this one squared. And finally, we multiply this one with this one and we get this one. Okay, these 5 columns. We have to just put this in a calculator and integrate it. Alright. This one would m into m dv. This one would give us delta d. This one would give us theta d. And the m dv square. This one will give us so on a small point c. So This one will have FCC. Sorry, this one, all of these points were C points. So MCV square, C theta square, C alternate D. So this one will give us point FCC, flexibility at CC, and this one will give us alpha CC. Finally, this one will give us both of these. This. So CV, you can write it as F CV C theta or alpha. This is one is rotation produced by vertical force at CV. Okay. So basically we get the 6 variables. We have 3 and 3. We have these 6 unknowns, 6 variables. We calculate these values of deflection from this table. Okay.
Okay.
All right. So finally, let's do this for this third case. This case will have almost 9 plus 13 equations, 13 columns. So first to remember, then origin, then limit. These three are must. Then we are writing M for primary structure moment equation. Then this one is MD, horizontal, vertical, and moment. So we can write MDH, MDV, MD theta. So these columns are just we are writing equations. Moment equation for primary structure, for where the horizontal load is applied, where vertical load is applied, and where unit moment is applied. Afterwards, we are going to multiply them. So first multiply M with these individually. So we'll get M into MDH and integrate it. Second will be M into MDV integration, M into MD theta and integration. Then we'll square these individually. So MDH whole square, MDV square, MD theta, square. And finally, we'll have multiply these with one another, MDH into MDV, MDV into MD theta, and MD theta into MDV. So we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 4, 13 columns. Okay, we'll have to calculate 13 deflection in this case. This one would be delta DH horizontal deflection, delta DV vertical deflection, and theta D rotation at D. These are all for primary structures. And from this we'll get FDH, DH, FDV, DV. We'll calculate all these values and sum it at the end. Then we'll get this coefficient, flexibility coefficient, alpha DD. And here DH into DV, so we'll get FDH, DV, FDV, DH. Here we have dV into d theta, we'll get F d delta by dV, and moment at d alpha into dV. Sorry, no. We get F dV alpha d. Vertical displacement by moment at d, and here we have rotation caused by dV force. So here dH, F dH by alpha d, and rotation by at t point by horizontal force dH. Okay, these are our knowns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll place them back in this equation. 12 unknowns. 1, 2, 3, and we can expand them like this. Theta d plus alpha d delta dh into dh plus alpha d delta dv into dv plus alpha dv into md. So we'll get like this one, this one, this one, and similar we'll get flexibility for these, all these. Okay, from these table. Is that all right?
Yes, yes.
Yeah.
Oh. So basically, we have these 3 steps. Only we have to get done. We have done these 3 steps. These are we can say these are the new 1 steps. The rest is simple. After we have suppose, let's consider frame. We have calculated force at, no sorry, we have placed value here. We can simply solve it simultaneously in a calculator. It can solve up to 3 equations. If your calculator doesn't have, just go to the matrix option and write down the coefficient of these terms as matrix A and write down these delta values as matrix B, and simply take the inverse of A and multiply it. What I'm trying to say, you can do this like this: Ax is equal to B, x is equal to A inverse of B. So we can calculate a quotient matrix and our right hand side matrix, take inverse of quotient matrix and multiply them with B matrix. So we'll get the values of, from here we'll get the values of HD or DH, VD and MD. After we have calculated these values, we know this is PV or VD, HD and MD. We have calculated these values. We can simply use equilibrium equation, summation moment at something at A is equal to 0. This one was A. And we can calculate MA here. Then we can use summation Fy is equal to 0, calculate VA. Then similarly summation Fx is equal to 0 for HA. After we have done this, we have to draw the shear force and bending moment diagram. Okay, so this was all about force method. What we have to do is this. I'll try to quickly give an overview again. First, we have calculated primary structure as well as unit structures. Then we have written the compatibility equations, and then we calculate deflection by unit load method. Then reaction and shear force and bending moment diagram. So for first, we have to check the degree of indeterminacy of beam or frame, also truss. For truss, the method is almost same, but there is just one difference. So for beams and frame, we have calculated degree of indeterminacy. Then, depending on that degree of indeterminacy, we derived how many redundant structures should be there. So if the degree was 1, we write 1 structure. If it was 2, then we have written here 2 structures. Here 2 structures, we have tried 2 structures, and if the degree was 3, we have written 3 redundant structures. So we have resolved the question into a primary structure as well as redundant structures. Then we have to then we can label these like these. We have to label these deflections. It will become much more simpler to solve. Then we write the compatibility equations. So after these, we have to calculate the unknown variables in these equations, which we can calculate by unit load method, like I don't know where it has gone. Oh, here. So we can use unit load method, and we can calculate the deflections. We put it back in the equations, and then we calculate the unknown forces. Suppose we have DH, AG, and MD. We calculate these forces. Then we use the equilibrium equations to calculate all the other which were unknown. For example, we have HA, VA, and MA unknowns. So we calculate these ones. And finally, we have to draw the shear force and bending moment at once. All right. So any questions?
No question, Hamza.
No question? Oh, okay. Did you understand something or has it gone all over the head? Did you learn something new? Or not?
Azhan, what about you? And I think I hope to go through some numericals, and inshallah I'll contact you further if I had any doubts or any
All right,
issues.
of course. I'll try to share what I've written. Numericals. You can also contact me.
Okay. Jazakallah khair.
All
Share
right,
it.
thank
Okay,
you.
brother.
All
What
right.
is it possible for
Thank you so much.
how to
Thank you so much.
Thank
No
you.
problem.
Yes,
Okay,
yes,
you
okay,
had
no
thank
problem.
or steel structures?
Steel or sorry?
Yeah. I mean, if you had enough time, and how to have an overview, and to do numericals on steel structures.
All right, all right. We can try to go it on. Actually, we are very. I was also doing today the
Yeah.
assignment of essay.
Yeah.
All our teacher are given assignment so near to the papers. We have to
Yeah,
submit
yeah.
one for hydro on Friday. So we can try it for on Wednesday. That's all right with you guys.
Okay, inshallah.
All right.
When it
All
will
right. Sorry.
when it will be convenient to you on Wednesday at what time? Probably.
Same time. 7.
Okay,
All
inshallah.
right. All right. Thank you for having.
Jazakallah khairan.
Thank you, Hamza.
Thank you.
Thank you.
Okay.
Thank you,
Take
brother.
care.